Hello students, in our last class we derived a relation for work done in isothermal and reversible expansion of ideal gas. Based on that, we will do one numerical, calculate the amount of work done by 2 moles of an ideal gas at 298 Kelvin in a reversible isothermal expansion from 10 liter to 20 liter. So, according to the data given, so N is here, N is 2 mole and V1, that is the volume, 10 to 20 liter. So, 10 liter, and then V2 is 20 liter, okay, and we have to calculate the amount of work done. So, amount of work done for isothermal, that is expansion of in a reversible process is given as, we know, work done is equal to minus 2.303 nRT log V2 by V1. Okay. So, here work done is equal to minus 2.303, N is 2 mole into R is, that is the gas constant, 8.314 joule K inverse mole inverse into temperature is, that is 298. So, 298 into log of, that is V2 is 20 by 10. So, that is log 2 is 0.3010. So, we will substitute here. So, minus 2.303 into 2 into 8.314 into 298 into 0.3010. So, when we calculate, we will get the answer as 3434.9 joule. So, this is the ideal gas, that is work done by 2 moles of ideal gas in a reversible isothermal expansion. Okay, students. So, students, energy changes that takes place in a reaction at constant volume and constant temperature is given as del U is equal to QV, where Q is the heat absorbed or evolved at constant volume, is given as del U. So, we know that all the reaction is carried in a open system, that is in an open tube or open container, where the changes in volume takes place and the pressure, that is the atmospheric pressure, is kept constant. Okay. So, the energy changes that takes place is may not be equal to the internal energy. So, we have to derive a system that is which is at constant pressure. Okay. So, according to first law of thermodynamics, we know that is del U is equal to Q plus W. Okay. Now, del U at constant pressure, that is minus P del V. Here QP is heat absorbed at constant pressure, okay, and minus P del V is work expansion by the system. Okay. So, this is work expansion by the system. So, now we know, suppose a system does the work, that is, suppose system does the work, that is QP joules of heat Qp joules of heat is absorbed. Okay, so Qp joules of heat absorbed. So the internal energy, the internal energy will change. That will be U1. That will be U1 to U2. Okay. Similarly, the volume, that is also changed. So that is, it will change, that is V1 to V2. Okay. Now we will substitute to this equation. So this equation, that is del U is equal to Qp minus P del V. In this equation, we will substitute the change in internal energy, that is increase in internal energy and increase in volume. So U2 minus U1 is equal to Qp minus P V2 minus V1. Okay. So the system, that is Qp joules of heat is absorbed. So the internal energy also changes, whereas the volume also changes. Now this can be further written as Q2 U2 minus U1 is equal to Qp minus P V2 plus P V1. Okay. Now on rearranging, we will get, that is Qp is equal to U2 plus P V2 minus U1 plus P V1. Okay, students. Now we know the U, P and V, they are state function. Okay. When they are state function, so the quantity that we got, that is U plus PV, must be a thermodynamic state function. So this is also a state function. Okay. Now this must be also a state function. Now this U plus PV is nothing but it is H, and this H is heat content, that is heat content of the system. Okay. Or in Greek it is said as enthalpy, Greek word, it is said as enthalpy of the system, of a system. Okay. So that is H2 minus H1 is nothing but it is Qp. Okay. Now here I will substitute that as H is equal to U plus, here I will substitute as U plus PV. Okay. So delta H is equal to delta U plus delta PV. So here P is constant. Okay. P is constant, that is pressure is constant. So del H is equal to del U plus P delta V. Okay. That is P delta del H is equal to P delta V. Okay, students. So this is the change in enthalpy, change in internal energy and change in that is volume. So change in volume. So we got, that is delta H is equal to delta U plus P delta V. This is enthalpy change. Okay, students. So students, delta H is equal to delta U plus P delta V. So here delta H is negative, then it is exothermic reaction. Exothermic reaction. Okay. Whereas when delta H is positive, it is endothermic reaction. Okay. Now delta H is equal to delta U at constant volume, so delta V is 0. So this will be 0. So delta H is equal to delta U, that is QV. So we know that is the difference between delta H and delta U is not that significant in the case, that is change in volume is not that significant in the case of solid and liquid, and it is more significant in gas. So now we will consider a system that is a gaseous system in which the gaseous changes in which the changes takes place. Suppose consider a reaction in gaseous state. Okay. Now reaction, that is A gas gives B gas. So this is reactant, and this is product. Okay. So let total volume of gaseous reactant be VA. Similarly, total volume of gaseous product be VB. Okay. So the number of moles, similarly the total number of moles of gaseous reactant can be given as Na. Okay. Now the total moles of product, gaseous product B NB. Okay. So NB. So from ideal gas we know PV is equal to nRT. Okay. So we are considering a reaction in a gaseous state. So so this will be changed and this also will be changed. So for first equation, we will write as P VA is equal to NART. This will be 1, and similarly P VB is equal to NBRT. This will be 2. Okay. Now subtracting 2 with 1, that will be P VB minus P VA is equal to NB RT minus NART. Okay. Now this and this are common, so I will take the P is common for both, that is VB minus VA. Similarly here RT is common, so I will take RT as common, so NB minus NA. Okay. So P, this is nothing but it is change in volume, P del V is equal to, then this is nothing but it is delta NG RT. So this is a change in volume from one state to another state, and this is that change that is the total number of moles, that is change of number of moles from reactant to product. Okay. So in the place of P delta V, I will substitute this. So our equation will be del H is equal to del U plus delta NG RT. Okay. So this is the that is change in enthalpy is equal to change in internal energy plus delta Ng, that is total number of moles, that is Np minus Nr. Okay. Now we will see Np minus Nr into R into T. Okay, students. Now here three cases arises. Delta H is equal to delta U, delta H is greater than delta U, and delta H is less than delta U. Okay. For the first case, if suppose if a reaction, that is H2 gas plus I2 gas gives twice of Hi. Similarly, N2 gas plus O2 gas gives twice of NO. So here in the first case, this is number of moles, that is we know delta Ng is equal to Np minus Nr. So number of product minus total number of product minus total number of reactant. So here the number of moles of the product minus number of moles of the reactant. So here it is 2 and here 1 plus 1. So 1 mole plus 1 mole 2. So 2 minus 2 we have, that is 0. So which is 0, that is delta H is 0 in this case. Okay. Now for the second also similar, that is 2 1 plus 1 2. So this is delta H is 0. Okay. For the second case, delta H is greater than delta U. So delta H will be positive. Let us see, PCl5 gas gives PCl3 gas plus chlorine gas. Okay, the first case. Second case, N2O4 gas gives twice of NO2 gas. In the first case, that is delta Ng is Np minus Nr. So here it is 1 mole plus 1 mole. Okay, 1 mole plus 1 mole, that is 2 mole minus 1 mole. So that is 1, which is positive. Okay. In the second case also 2 minus 1, that is 1, which is positive. Is it clear? Now next is this one where delta H is negative. Okay, students. So here we will take example of, let us say, nitrogen gas plus hydrogen gas gives ammonia, that is NH3 gas. So we will balance 2 here 3. Okay. So second case, again SO2 sulfur dioxide gas with O2 gas gives SO3 gas. Okay. Now we will balance twice of SO3, twice of SO2. Now here delta Ng is equal to Np minus Nr. So here we can see 2, this is product is 2, number of moles is 2, and here 3 plus 1, which is 4. So answer is minus 2. So delta H is negative. So in the second case also delta Ng is equal to Np minus Nr. So in the second case 2 minus 2 plus 1, that is 3, which is equal to minus 1. So we got that is minus 1 minus, so delta H is negative. So students, remember both internal energy and enthalpy are state functions, and they depend upon the state of the system and independent to the manner in which the state has been attained, yeah, brought. Okay. Now students, let us see a question. The reaction of cyanamide NH2Cn with oxygen was affected in a bomb calorimeter, and del U was found to be minus 742.7 kg per mole of cyanamide at 298 Kelvin. Calculate the enthalpy change for the reaction at 298 Kelvin. So here the reaction is given, that is cyanamide plus 3/2 of O2 gives N2 plus CO2 and H2. First we have to see in this equation, we have to see the state here it is in gaseous state, we have to consider the gaseous state only. So, here also then we will not consider this as in the reaction, that is H2O. Okay, it is in liquid state and here it is in solid state. So, first we will see delta Ng. Okay, delta Ng is del Np, number of moles of the product, minus number of moles of the reactant. So, here number of moles means 1 mole plus 1 mole, that is 2 mole, minus here it is in solid. So, we will not consider that, and we will consider this 3 by 2 as it is in gaseous form. So, 3 by 2. So, which is 4 minus 3 by 2, which is equal to 1 by 2. Okay. So, we got that is 1 by 2. Now, next is temperature. So, temperature is given, it is in Kelvin. So, okay. So, 298 Kelvin. Okay. 298 Kelvin. So, we will write the equation, that is delta H, that is change in enthalpy, is equal to del U plus delta Ng RT. Okay. Now, here del U is given as minus 742.7 kJ per mole. Okay. Now, so minus 742.7 kJ per mole or mole inverse plus now we got this as 1 by 2, that is total number of moles 1 by 2 into R is 8.314 into 10 to the power minus 3 kilo joule K inverse mole inverse. Okay. Now, temperature is 298. Okay, students, 298 Kelvin. Okay. So, with this Kelvin and Kelvin, this will be cancelled, mole and this mole. Okay, it will cancel. So, when we calculate, that is minus 742.7, that is kJ kilojoule, and when we calculate plus this one, this part when we will calculate, we will get, that is 1.239. So, this will be as when plus, this is minus and this is in plus form. So, I will take this 2. So, minus 741.5 kJ per mole. So, that is the required answer for this question. Now, students, next we will see this question. A swimmer coming out from a swimming pool is covered with a film of water weighing about 18 grams. How much heat must be supplied to evaporate this water at 298 Kelvin, and calculate the internal energy of vaporization at 100 degree centigrade. Okay, students. So, here the enthalpy of vaporization for water at 373 is 40.66. So, we have to calculate the internal energy. Okay. So, first we have to know that is process of vaporization, that is process of vaporization. Okay. Vaporization, we know that is H2O liquid to H2O gas. Okay. So, here number of moles, it has been given as 18 grams. So, number of moles of H2O in 18 grams, which is equal to given mass, that is 18 gram divided by 18 gram per mole. Okay, students. So, which is, that is 1 mole. So, we got 1 mole, and here that is enthalpy of vaporization is given as 40.66 kJ per mole. Okay, students. So, temperature is given as 373 Kelvin. Okay. Now, we know the equation delta H is equal to delta U plus delta Ng RT. So, now this has been asked and this is given. Okay. This all are being given. So, you can write as delta U, that is vaporization is equal to delta H vaporization minus delta Ng RT. Okay. Now here enthalpy of vaporization is as 40.66 kJ per mole, okay, minus 1 mole, we got 1 mole, okay. Now into R is 8.314 joule, so it will convert into kilojoule, 10 to the power minus 3 kilojoule, okay. K inverse mole inverse into 370, that is temperature 373. Okay, students. So when we multiply all this, we will get 3.10. So 40.66 minus 3.10. So it will be, that means 37.56 kJ per mole. So this is the required internal energy of vaporization at 100 degree centigrade. Okay, students. Now we will see one more question based on the similar type. If water vapor is assumed to be the perfect gas, molar enthalpy change for vaporization of the 1 mole of water at 1 bar and 100 degree centigrade is 41 kJ per mole. Calculate the internal energy change when 1 mole of water is vaporized at 1 bar pressure at 100 degree centigrade. So we have to change, first we will change to Kelvin. Okay, we have changed 100 plus 273, 373 Kelvin. Now delta H, that is delta H enthalpy change is given as 41 kJ per mole, that is molar enthalpy change. Okay, now Ng gas and it is in liquid, so 1 minus 0, that is 1 mole. Okay, now we know that is delta H is equal to delta U plus delta Ng RT. So we have to find delta U. So we will shift to the other side, that is delta H E minus delta Ng RT. So 41 kJ per mole minus 1 mole into, when we multiply all this we will get 3.10. Okay, so when you subtract 41 with 41 we will get this as the answer, that is kJ per mole. Okay. So the next part, it has been asked as internal energy changes for the conversion of 1 mole of water into ice. So this is ice, okay, and this is water. So this is water. So to convert it into solid. So here delta Ng is 0. We will be considering for gaseous states only. We are considering for the gaseous state, this total number of moles for the gases. So this will be 0. So when it is 0, this part is completely 0. So this part is 0. So delta U is equal to delta H. So delta U is equal to delta H, that is 41.00 kJ per mole, that is 41.0 kJ per mole. Okay. So students, we will deal with the next topic in the next class. Thank you very much.